Hi, welcome. This is Measure Theory 29th session, Lp-Spaces-2. In the last session, we discussed about the space of integrable functions, L1, after getting L1 consists of equivalence class of integrable functions. Okay, we define a norm and we also looked at what does it mean to say Fn converge to F in L1. Okay, it does not, what we saw is, it does not guarantee if F1 converges to F in L1, F1 converges to F point-wise even almost everywhere. And if F1 converges to F uniformly, does not mean F1 converges to F in L1. That also we saw. Okay, right. So today what we want to do is we want to prove under this norm or under this metric, L1 space is complete. Okay, this proof is very interesting. And we will also extract the idea of the proof, okay, formulate as a general result later. Okay, then we shall look at some of the dense subsets of L1 if all these things, if time permits. So we are fixing a measure space X mu measure space, and recall L1 of Ax b mu and this L1 of X b mu are different. These are all integrable functions. This is equivalence class of integrable functions. But still, we will only write as F, we will not write this, okay? We will write this as well. All these conventions I already explained in the last lecture. So what we want to show is, if Fn is a Cauchy sequence in L1, I will simply write L1, okay? Then there exists an F in L1 so that Fn converges to F in L1. Okay, what does it mean? Fn is Cauchy simply means given me any epsilon, there is an n, so that for all m and n greater than or equal to n, the distance between Fn and Fm, this is nothing other than distance between Fn, this with respect to the L1 norm, this should be less than epsilon. Okay, and what does it mean to say it's Cauchy? For any given epsilon, there is n, so that L1 norm of Fn minus F, that is distance between Fn and F, is less than epsilon. Okay, these are the standard definition. Now, why this is important? You may recall in a metric space, at least if you have studied my book or watched my videos, okay, if you look at C of 0, 1 or in general C of AB or anything, okay, and if I define for a continuous function the L1 norm as above mod f of t dt AB, this is nothing other than the integral mod f of dm over the interval AB, the Lebesgue integral. They are the same. Okay, we know this is not complete. Okay, this is well known. Okay, look at my book for example. Okay, so what we are going to show is this is the, on the other hand, the set of integral functions is going to be complete. Okay, the proof is interesting. What is the idea of the proof? Strategy is the following. We will first show there exists a subsequence, let Fn be Cauchy. In L1, I want to say there exists a subsequence Fn k so that Fn k converges to F point-wise almost everywhere. And this F belongs to L1. Okay. Then from this we conclude my Fn k converges to F in L1. Right? And this is a very general result in metric space. If xd is a metric space, xn is Cauchy. This is what you might have seen in real numbers. If x and k converges, then xn converges to the same x. Okay, at least in real analysis you would have seen, and the same proof works for any metric space. That is, if I have a Cauchy sequence, if it has a convergent subsequence, then the original Cauchy sequence converges to the limit of the subsequence. Okay, so we will therefore f and k converge f in L1. F and k is a Cauchy, okay, subsequence of the Cauchy sequence. Therefore, it will follow f and converge to f in L1. This is the strategy. Okay, pause, review, proceed. Now, how do I get the convergent subsequence? So let us look at. Since F1 is Cauchy in L1, okay, for if I take epsilon equal to half, there is an N1, so that for all m and n greater than or equal to N1, L1 norm of Fn minus Fm will be less than half, right? Now what I do is, for epsilon equal to 1 by 2 squared, there is an N2. I can also choose N2 greater than N1, so that for all n greater than or equal to N2, this is less than 2 to the power minus 2. Do you understand this? Right? Therefore, in general, for epsilon equal to 1 by 2 to the power k, that is 2 to the power minus k, there is nk, which is greater than nk minus 1, so that for m and n greater than or equal to nk, fn minus fm is less than 2 to the power minus k. Right? So I have a subsequence now, f and k. Right? Notice that in particular, norm of f and k minus f and k minus 1 will be less than 2 to the power minus k, because nk is greater than or equal to 2 to the power k, sorry, nk plus 1 is greater than 2 to the power minus k. Yeah, so I have nk, and therefore this must be at least this much, right? In particular, this means f1 minus f and k must be less than 2 to the power minus k. Now by chance, nk plus 1 is greater than nk, therefore I can apply this. Is that clear? Okay, right? So we want to show f and k is convergent in L1, that is to some function. Okay, for that what we do is something very interesting. Okay, what we want to do is, again, first we want to say f and k is pointwise convergent to some function, some, of course, necessarily measurable function. F may or may not be in L1, may not be in L1, but we will finally show it is in L1. At present, I do not know. I just want to show its pointwise convergence, right? What is the strategy? Again, this has a strategy. What is the strategy? The strategy is, recall Levy's theorem. So if Fn, this is not this Fn, some other Fn, Fn's are non-negative measurable, and then we have shown that this equal to the, right? This is Levy's theorem. And next thing is, this is one idea. The second idea is, if f is non-negative and integral f d mu is finite, then f is finite almost everywhere. Okay, these are the two results we already know. Okay, we want to use that. Okay, so the way we want to use is the following. Let me define gk it to be fn1 plus summation fn j minus fn j minus 1 j equal to I want to fn1 2, it should get cancelled, therefore it equal to 2 to k. So let me write it fn1 plus fn2 minus fn1 plus fn3 minus fn2 and so on plus fnk minus fnk minus 1. Yeah, notice that each gk, all these things are in L1, therefore gk is in L1, right? And what is norm of gk? Norm of gk is less than or equal to norm of fn1 plus summation of norm of fnk, let me write fnk, okay, fnj minus fnj minus 1 and j equal to 2 to k, right? But notice that each of these fellows will be less than 2 to the power minus j minus 1 or whatever it is. Okay, j minus, okay, 2 to the power minus of this fellow, that is minus j plus 1, right? Therefore, you know that, okay, this is finite. Yeah. So, therefore, if I look at gk, right, therefore, now of gk, k equal to 1 to infinity is finite. Is that clear? Pause, review, proceed. Therefore, let's look at this. But what is this? Integral, okay, infinity is greater than norm of gk. These are all L1 now. Okay, I will not write it because we are concentrating only on L1 now. This is equal to summation of integral mod gk d. Right? This is okay. Now I can use Levy's theorem. Okay, this says this is same as integral of summation mod gk d. Okay. Now this means this is convergent. So call this as capital this g, where g is summation mod gk, that is g of x equal to summation mod gk of x. Okay, this function is integrable. That's what it says. Therefore, g is positive and g is in L1. Therefore, by second result I quoted, g is finite almost everywhere. Pause, review, proceed. Now, since g of x, so let z be the set of all x in x such that summation gk of x is not convergent. Okay, this is not convergent. So what we know is measure of z is 0. Okay, therefore let me define f of x equal to summation gk of x, okay, for k equal to 1 to infinity, x is not in g, not in z, equal to 0 otherwise. Right? Now since for z not in, okay, for z not in z, we know mod gk of x, this is a series, okay, this is absolutely convergent, therefore the corresponding series must be convergent, therefore this belongs to R or C or whatever you want. Okay, you understand that? Yeah, therefore we turn out to be f is measurable, right? And the next thing is, I claim f and k of x converge to f of x almost everywhere. So why? Now let's look at what is gk of x. Gk of x, k equal to 1 to n, is fn1 of x plus fn2 of x minus fn1 of x and so on, plus fnk of x minus fnk minus 1 of x. So you can see all these things will get cancelled. This will cancel, and therefore what I am left with fnk. Right? But what I know is k equal to 1 to n of gk of x converge to f of x. Because what is f of x? That is by definition gk of x, k equal to 1 to infinity for all x in z, not in z. You understand? Yeah. Therefore, what you have concluded is, therefore, the subsequence f and k of converges to f pointwise on x minus z. Okay. Now what we want to claim is f and k converges to f in L1. Yeah, but I want to say why f is in L1. Why is f in L1? Yeah. Notice that each f and k, mod f and k, is less than or equal to, or whatever it is, mod gk, but that's less than or equal to mod g, and this g is mod g, which is g, and this is in L1. Therefore, each f and k is bounded by an integrable function, and f and k converges just to f pointwise. Therefore, mod f is also less than or equal to g. Of course, for all x in, not in z. That's good enough. Okay. So mod f is bounded by a integral function almost everywhere. Therefore, f is L1. Next, I want to say f and k. Okay. F and k converges to f in L1. Okay. So what does that mean? I have to say in norm of f and k minus f in L1 norm, that goes to 0. Yeah. But remember, f and k converges to f pointwise almost everywhere, and f and k is dominated by g, where g is in L1. Therefore, by dzt, dominant convergence theorem, okay, modulus of f and k minus f goes to 0. That means that is f and k converge to f in L1. Okay. Therefore, what have we shown? So we have shown, given a Cauchy sequence fn in L1, we have an L1 function f1 and a subsequence f and k which converge to f in L1. Therefore, by the result which I quoted from real analysis or metric space, see, okay, whenever I have a Cauchy sequence and if it has a convergent subsequence, the Cauchy sequence also convergent to the limit of the subsequence. Therefore, we conclude f and converge to f in L1. Since fn is a Cauchy or any Cauchy sequence, and we have shown any Cauchy sequence converges, therefore we conclude x1 is complete. Okay, this proves the result. We see the proof is very, very interesting. Yeah. So, what are the things we wanted? As I said, the strategy is if you give me a sequence f1, Cauchy sequence, you find a convergent subsequence in L1. Okay. To show that I can find the convergent subsequence, what we did is something very interesting. We use the Cauchy nature, okay, to find a sequence nk of increasing sequence of natural numbers such that norm of f and k minus 1 is less than 2 to the power minus k plus 1 or whatever. Okay, right? Now from this f and k, we used it to construct a gk or gn equal to fn1 Yeah, since that's why n comes here, therefore let me call it gk. Gk equal to fn1 plus fn2 minus fn1 within bracket plus so on. The last one only within bracket fnk minus fnk minus 1. Okay. Then what we showed is this summation gk, okay, is the norm of this, okay, L1 norm of summation, norm of gn gk, that is finite. Okay, therefore use Levy's theorem. It's a very interesting proof. Please go through it. Okay, this is the simplest way one can do that. Okay, if you understand the strategy, then you will be able to recall the proof much easier. Otherwise, it looks a lot of technical results. Okay, please go through it. But there is a very interesting thing. The proof actually shows something much more. Okay, I will say that the proof, the first part of the proof, okay, says if X is a non-linear space, if I have a sequence xn in X so that norm of xn is convergent, implies this is convergent. What does this mean? This means x1 plus 2xn, this sequence of partial sums, there exists an x in X so that this converges to x. Then we write it as xn equal to 1 to infinity equal to x. We call it the sum as we do in the infinite series of real numbers, right? So if this is something like absolute convergence. Absolute convergence implies ordinary convergence, right? In real analysis, you need completeness of R to prove that. Here, what it says is this, okay, whenever this happens, for every sequence xn, so that summation of norm xn is convergent, implies the series of vectors, summation n equal to 1 to infinity xn is convergent. That is guaranteed. Then x is complete. Okay. So I have produced a separate video on this under the name when a norm linear space is complete. Okay, it will be under the playlist functional analysis. I will include a description. Okay, the URL, okay, is in the description for this video. Okay, so this is an aside. If you are not or don't want to learn nothing, it's okay, you can ignore. Okay, now the next result what we want to do is we want to talk about dense subsets of L1. Remember this, as I keep emphasizing, either in metric space or real analysis or general topology, why we want to talk about dense sets. Okay, never think of A closure equal to X as the definition of density of A in X, but you should think of, at least in the metric space concept, any X can be approximated by a sequence A and coming from A, the dense set. Okay, so that is the most important thing, right? L1 is very good, okay, but it may be very weird. There are a lot of things. So what it want to say is I want to see there are a lot of interesting class of functions which are dense in L1. So for most often I can use it. In fact, I will give two such applications because these are the things which are never done. They will only say it's separable, etc., density, etc., but they don't say why they are important. Okay, we are going to do that if time permits. Okay, so stay tuned. We will start. We will continue. So even here, let me just make sure that we are starting. Yeah. Even here, there is two important facts which will keep playing. Suppose XD is a metric space. Okay, D is a dense subset. What does it mean? For every given any x in X, there is a sequence an in D, so that an converges to X. This is my definition. Okay, right. So this is D is a dense if only this happens. Okay, right. Suppose I want to say a subset A of X is dense. Okay, then it's enough to show for every epsilon given any X in D, okay, and epsilon positive, there exists an A so that distance between A and X is less than epsilon. If you want to call it D, that G will confuse with D, so let me write X itself. Okay, there is that. Right? So intuitively it should be obvious. What does it say? See, any element D approximates any element, any X in X. Right? Now A approximates any element in D. That's what this says. Right? Therefore, I should expect A approximates X, any element X. Okay. If you want a rigorous proof, it's very easy. Okay. Assume. Okay. This is true. False. Okay. Now let Y be any element in X. Okay. Then I know for the given, let epsilon be given. Okay. Then for epsilon by 2, I know there exists an X in D such that distance between X and Y is less than epsilon by 2. Now, for the same epsilon by 2, there is an A in A such that distance between X and A is less than epsilon by 2. Therefore, the distance between Y and A is less than or equal to distance between Y and X plus distance between X and A, which will be less than epsilon. So we proved it. You understand? So pause, review, proceed. So what is that we are saying? If D is dense and if A approximates every element D, then A also is dense in X. Okay? Right. That's a very easy one to believe. The second one, suppose I am in a non-linear space. This is X is a vector space and this is a norm. Right? There is something very interesting. Okay? Suppose I have a set D which is dense in X. Right? So to prove A, what I can do is something very interesting. Suppose this is a vector subspace. Okay, this is not in a set, it's also a vector subspace. Are you following? Right? Okay. Now what I want to claim is suppose A is a subset of X, right? And for every X in D, okay, and for every epsilon positive, there is an A in A such that distance between X and A is less than epsilon. Right? Then notice that okay, given any element, given elements x1, xn in D, okay, then I can find a1, an. I may look at x1 plus xn. Okay, I want to look at this element x. Okay, this is in D. Right? Then there is elements a1, given epsilon positive, there exists elements a1, an in A, so that distance between xi and ai is less than epsilon by n. Right? Notice that this is nothing other than norm of xi minus ai for all I. Right? Therefore, if I take a equal to a1 plus an and x equal to x1 plus xn, right, then norm of x minus a equal to norm of x1 minus a1 plus norm of x1 minus an. Right? Do you understand this? x1 plus xn minus a1 within bracket a1 plus an. I regroup the terms, I get this. But that's like that equal to x1 minus a1 plus xn minus an. That is less than n times epsilon by n equal to epsilon. Right? So what does it say is, okay, we can make use of the non-linear structure, vector space structure in computing the density, in showing something which is dense. Just pause, review, just internalize this. We are going to make use of it, then you will find it much easier to understand the proof. The first thing is the set of bounded functions in L1 is dense in L1. See, for example, if I take L1 of R M mu, the constant function 1 is bounded, but 1 is not in L1. That is why we are saying, look at only set. Therefore, what is the set I am considering? The set I am considering is F is L1, but F is bounded. That's it. Okay. I want to say this is dense in L1. We had already seen this after as an application of DCT. Perhaps this is the first application of DCT. Okay. Right. Now suppose give me any f in L1. Right. Then we define for each natural number n, we define fn of a to be fn of x equal to f of x if mod fx is less than equal to n if mod, okay, otherwise. Okay. Do you remember I call this truncation? F at truncation of f at n. Okay, the picture is something like this. So this is my n to minus n. So here also the picture will be here. Okay, the picture will be only this. The graph will be only this. Like that. Okay, this is the truncation. So notice that f n of x converges to f of x pointwise, and each f1 is bounded by n, right? Now notice that also f n of x is less than equal to modulus of this is less than equal to f of x. Now f is in L1, right? Therefore, I have a sequence of measurable function which converges to f of x, and it converges in the dominated way because all these things are dominated by f1. Therefore, what do I know? I know integral of mod fn of x minus f of x du mu x goes to 0 by dct. Right? Therefore, given epsilon positive, there is an n, so that for all n greater than or equal to n, is less than epsilon. In particular, f capital N of x, okay, f capital N minus f in L1 norm is less than epsilon. So we have proved the set of bounded functions in L1 is dense in L1. Okay, pause, review, proceed. And second dense subspace is, let's look at the set of simple functions in L1 is dense in L1. Again, the same remark says, right? Not all simple function may be in L1, but look at only those which are in L1. Then I want to say this is dense. How do I prove that? So let us start with an f in L1. Assume f is greater than or equal to 0 to start with, right? Then I know there is a sequence Sn, okay, of simple functions, and such that they are all non-negative and they increase to f, right? Therefore, what I have? Therefore, now notice that mod Sn's are negative, therefore non-negative, therefore less than or equal to f. F is in L1, and Sn converges to f pointwise. Therefore, by DCT or monotone convergence theorem, interrelation, okay, may make a DCT, Sn minus f goes to 0. That means for all there exists n, so that for all n greater than or equal to n, norm of Sn minus f is less than epsilon. Given epsilon, there exists n, so that for all n greater than or equal to capital N, this happens. Therefore, we have proved the result. Right? Note that both these results are in any arbitrary measure space. Yeah. So this is fine. I'll just, in fact, I want to talk about little N1, capital L1. L1. I forgot one important example. Let us have a look at. Okay, it's a digression. See, this is how I think. I'm sorry, I don't come prepared, so they have to do something. Okay, but that's a very important example, and also it sheds the light on various things which you are discussing. Okay, I hope you don't mind. Let us have a digression. Suppose I start with n and mu is a counting measure. Then we have seen that f from n to r or c is integrable, that is in L1, if and only if summation mod fn is convergent. Okay, we proved it for positive function, but the same thing is true, because if f is integrable, if only mod f is integrable, therefore mod f is non-negative function, therefore this result follows. Right? Now, as a dense set, can you think of a dense set? So this usually capital L1 of n p of n mu is denoted by little L1 in functional analysis. Okay, what does it mean? There they will define little this L1 equal to set of sequences an such that an is absolutely convergent. That's what we got. Okay, you define f of n to be an, then we got it. Okay, very easy. The thing is, let us look at that subspace W, which is okay all f in L1, so that f of n is 0. There exists capital N, so that f of n is 0 for all n greater than or equal to n. Right? Think of this as sequences. This means this sequence is eventually 0 sequence. That is a1, an minus 1. After that 0, 0, 0. Okay, that's all it means. I am writing mod, but it simply means f n is 0. Okay, I say W is dense in little L1, which is capital L1 of n, p of n, counting measure mu. But this is obvious, right? This is where what I said will turn out to be useful. Let us look at, suppose you give me an f in L1, notice that f corresponds to an. Yeah? It's a function whose value at n is n, a n. Okay. Then I define a g so that fix given epsilon positive. I know this mod of fn, this is convergent. Therefore, there exists an n so that if I look at Tn to be summation mod of k equal to 1 to n, the nth partial sum, okay, so then for all n greater than or equal to n, okay, this Tn minus this 1 to infinity of mod f n is finite. Notice that this is nothing other than mod of fn 1 to infinity minus Tn. I'm sorry that I'm using the same thing. Let me write tk. Yeah, right. This is the partial sums. Partial sums go increases to this, right? Therefore, this has to be less than epsilon, right? You understand this? Therefore, I define my g of k equal to be f of k if what less than equal to k less than equal to n and equal to 0, right? Then this g is in L1, which is L1 of n, mu, right? And what is the L1 norm of f minus g? This is by definition mod fk minus gk, k equal to 1 to infinity, but that is going to be n plus 1 to infinity of mod fk. Okay, that is less than epsilon, right? Are you following? So I have proved the set D, which is set of f in L1 of n, so that there exists n, so that f of k is 0 for all k greater than equal to n. This is dense in L1. And notice that this is a vector subspace, right? Now let me look at another thing, a set A, which is f in L1 of n, okay, or f1 in D, so that f of k is takes values only rationals for every k in n. You understand that? Look, in other words, in the terms of L1, this simply means this is all an, so that an is eventually 0 and ans are all rationals. That's what it means. Now you claim A is dense. In L1 of n, which is little L1. Right? Why I am doing this? See, when you go to functional analysis, you will learn these things. But in measure theory also I am doing. Do you remember what I said earlier? There are two tricks. One is this: if D is dense in X, and if I can show that A approximate every element of D, then A is dense in X. And the next thing is something to do with vector non-linear spaces. If I say D is a vector subspace which is dense, if I find A, I want to show it is dense in D, okay, I want to do something. Similar is what I want to do. Similar thing, okay. So this is dense in L1. So the way we do that is, given any, let us say given any A, n in D, right, then I know there is an Rn given and also given epsilon positive, okay. So assume that an is D, therefore there exists an n, so that ak is 0 for all k greater than equal to n, right? So only these terms matter. Make it n also. An may also be 0, let us say k greater than equal to n. Okay, right? Then for each a1, I have a rational number r1, which is something like given an epsilon positive, there is an R1 irrational number, so that R1 is close to A1. Similarly, Rn which is close to A1. Right? Now this is a finite thing, therefore I can say for each I, choose Ri in Q, so that modulus of Ai minus Ri is less than epsilon by n. Right? Then define R to be R1 to Rn, after that 0, 0, 0. That is, R is of capital L1, so that R of K equal to Rk for 1 less than equal to K less than equal to N equal to 0 if K is greater than N. This is the notation of capital L1. Is that clear? Now, notice that the distance between R minus my A is summation Ri minus Ai, I equal to 1 to infinity, but then this is I equal to 1 to N of Ri minus Ai plus 0, 0. Right? N plus 1 to infinity. But this is less than epsilon, because each one of them is less than epsilon by 2. You follow that? So if I directly want to show this set, okay, A is dense in L1, it may be difficult. So what I did was, I proved D is dense in L1, then I approximate each element of D by A. Okay, that's digression is over. Okay, those who kind of wanted could have passed forward. Now you stop and then again start. Okay, right. Okay. The next thing I want to show is I want to specialize to R Lebesgue measure, and okay, this one. Right? Now I want to define the set of continuous function with compact support. Okay. Is dense in L1 of R. So let us recall, I have a function f from R to R. What is meant by the support of f? Support of f is take the set of x in R so that fx is not equal to 0. Notice that this is an open set. If f is continuous, this will be open. Therefore, take its closure. Therefore, it's the closure of the set. So for any f also, we define to be the closure of the set. Do you understand that? F is any function, not necessarily continuous. Let us look at the set of x and R so that fx is not equal to 0, take its closure. Then we call it the support. Okay? Right. So this we want to say, this is compact. This is a closed set, we want it to be compact. That means it's bounded. What does that mean? This simply means f of x, there is an R positive, so that f of x is 0 if mod x is greater than R. Because any compact set is bounded, right? Therefore, for any x here, it has to be fx must be 0. Okay. The way to prove that is what I did earlier. Now we know, okay, the set of simple functions, let me call it yes, the set of simple functions in L1. Is dense in L1. Right? Now, notice that this will be a vector space. Right? Therefore, if f belong to S, may make it G. If G belong to S, right, then G is the form summation Ck indicator function of some Ek, where Ek is measurable. And let us this be the standard representation, right? Since G is in L1, right, and interval of G, mod G is going to be mod Ck into measure of Ek, summation K equal to K, summation over K, right? This has to be finite, right? Therefore, what does it say? If Ck is not 0, then measure of Ek must be finite, right? Therefore, we will assume if I write G equal to summation Ck I of Ek, this Ck is not 0. Okay, you take the standard representation, and in that, if Ck happens to be 0, throw it out. That's all it means. You understand? Standard representation minus the term where Ck is 0. Is it okay? Right? Then now this belongs to S, which is dense. Okay, this is dense. Right? So the trick I want to do is, given I of E, where measure of E is finite, okay, I will approximate this by a continuous function. Okay, there is a continuous function with compact support, so that F minus I of E is less than epsilon. For any given epsilon, there is a continuous function with compact support that is less than epsilon. Do you understand this? Right? By this kind of argument, which I did for little L1, and the point which I mentioned here, the second trick, in the case of non-linear spaces, we have a better way of looking at. Okay, therefore, this will show that it's enough to show any integrator function of a finite measurable set, that not a finite set, a measurable set whose measure is finite. Okay, that can be approximated. Okay, so I think we are running out of time, so I will just finish this proof. It's very easy. Here, this is where we need regularity. Okay, now measure of E is finite, right? Therefore, there exists an open set G and a compact set K, such that K is contained in E, E is contained in G, and measure of G minus K is less than epsilon. Right? Given epsilon, this is the regularity. Right? This is the inner regularity, this is the outer regularity. Okay? This is the inner, this is the outer. Right? Using, but this we had already seen earlier. Right? Now, by Urayson's lemma, okay, don't worry about normal space, etc. This is easy in the case of metric space. Okay, refer to my book. Okay, this is an easy thing. Okay, what does it say? If XD is a metric space and if A is a non-empty closed subset and B, so that A intersection B is empty, both are closed set, there exists a continuous function F from X to R, continuous, such as 0 less than equal to 1, and F is 1 on A and F is 0 outside B. On B. On B. Yeah? Right? So how do I use it? I have a closed set K and contained in G. Therefore, if I take L to be R minus G, this is closed and K intersection L is empty. Therefore, there exists a continuous function, right? Now let us look at this is my K, this is my G, okay, my E may be somewhere here. This may be my E, right? This is my K. There is a continuous function F from R to R so that F equal to 1 on K and F is 0 on F, which is R minus G. That means F is 0 outside G. Here it is G. This is my G. Okay, outside is my F. These are all my F. Right? Okay. Now I claim this F, what is the distance between this and this? This is by definition integral of fx minus I of x dmx over R. Right? Now notice that if x is in K, remember K is contained in E, E is contained in G. If x is in K, fx equal to I of x equal to 1. Right? Therefore, this is 0. Now, if x is not in G, that is outside, that is x is in F, right? Notice that since E is contained in G, okay, I of x is 0 and f of x is also 0. Therefore, this integral actually takes over only over G minus E, right? Fx minus I of x. Okay, and notice that my Z f is also less than or equal to 1. That's by Urysohn's lemma. Correct? Right? Therefore, this one is less than or equal to 1. This one will be at most 1. Therefore, this is less than or equal to measure of G minus K. G minus K. Right? So, 1 minus I of x is likely to be 0. Okay? May happen only for x in G. Sorry. Yeah, G minus K. I am not claiming for each x in G minus K, this object is non-zero. It may happen. Okay? Not 1, this is F. Okay? Therefore, what I have shown? We have shown that given IE, so that measure of E is finite, okay? There exists a continuous function with compact support, so that L1 norm of F minus IE is less than 1. For every epsilon, there exists something. Okay? Now, if you give me any simple function, yes, okay, right, which is in L1, then my simple function is of the form summation Ck indicator function of Vk, k equal to 1 to n, right? And measure of Vk is around finite. We already observed, right? Therefore, for each k, right, there is an Fk, which is a continuous function with compact support, so that norm of Fk minus indicator function of Vk is less than epsilon by mod Ck. Remember, I am assuming Ck's are not 0, right? And by this n also. Are you following? This is exactly what we did earlier. Therefore, if I look at my ck, fk to be my f, then f is a continuous function with compact support. And what is the norm of f minus summation f minus s? This will be equal to norm of ckfk minus cki indicator function of ek. That is less than or equal to summation mod ck into mod fk minus iek norm. But each one of them is less than epsilon by mod ck into n. Therefore, this will be less than epsilon. Right? Now, if you give me any g in L1, okay, then there for given epsilon there exists an s in s which is in L1, okay, so that norm of g minus s is less than epsilon, and for this s there exists an f in continuous function with compact support, so that norm of f minus s is less than epsilon. Therefore, you will get norm of g minus f will be less than or equal to norm of g minus s plus norm of s minus f, which is less than epsilon plus epsilon 2 epsilon. So we have proved in the case of R, the set of continuous functions with compact support is less than, so is dense in little l1, capital L1. The set of continuous functions with compact support in R is dense in L1 of R. This is what we have proved. Okay. Now the question I want to ask, what is the point of proving these density results? Okay. I thought I will have time to do it now, but I think I already exceeded, so I will do it in the next session. Right? So what are the things we have proved? To summarize, in a general measure space, we have proved set of bounded functions which are in L1 is dense in L1. The set of simple functions which are in L1 is dense in L1. These are the two things we proved. Right? Okay. In the third, what we did was in the case of R, Lebesgue measure, okay, there in L1 we proved set of continuous function. There is one more thing I should say. The set of, therefore, the set of simple functions in L1 of R will also be dense. The question is the set of step functions. Okay, do you remember step functions are what? Exactly like simple functions, except the measurable sets are going to be intervals now. Okay, that also is dense. We will prove it in the next, and then we will give applications of these things, because that is very important. It's not simply proving the results and be happy with that. We should say how to use it. Okay, we will do it in the next session. Okay, I hope you enjoyed. Take care. We'll meet again.